Ready for another deep dive. This time, we're going to go really small to see how the rules of the universe change at the tiniest levels and how those changes actually have an effect on the stuff we can see and touch.
It really is incredible to think about how those small particles and the quantum rules they follow can actually have an impact on the big stuff.
Yeah, that's what we're going to be looking at today. So let's just start with like the basics. Atoms are the building blocks of everything, right?
Right.
But what's going on inside of atoms that makes them so different from the world we see and feel every day?
Well, I guess a good place to start would be electrons. Those tiny little particles that have a negative charge and sort of orbit around the atom's nucleus.
I always picture it like a tiny solar system. Is that kind of right?
Yeah, a lot of people think that way, but the reality is actually a lot more strange.
Oh, okay. So spill the beans. What's the real deal with electrons?
Well, the thing is that electrons can only have certain amounts of energy inside an atom. Imagine it like a staircase, right? They can stand on one step or another step, but not in between the steps.
So you're saying that instead of like smoothly moving around the nucleus, they're jumping between these specific energy levels.
Yeah, exactly. And these jumps, these like quantized energy levels, are what makes the quantum world so different from the physics we normally experience.
So how does this staircase affect how atoms work?
It has a lot to do with how atoms interact with light. Like when an atom absorbs light, it can only take in specific amounts or packets of energy, which we call photons. It's almost like each step on the staircase represents a different color of light.
So that's why we see things as different colors instead of like a giant rainbow.
Right.
Because each type of atom has its own set of energy levels that determines what colors of light it can absorb and send out.
Right, exactly. And that's why every element has what we call its own spectral fingerprint, like a unique set of colors. It's all thanks to this quantized nature of light and matter. And it's not just some weird theory, it's actually the basis for technologies like lasers and LEDs.
Wow, so the color of the world around us is a direct result of these energy jumps inside atoms. Pretty cool.
Well,
But what about electrons themselves? I've heard that they can be in multiple places at the same time. Is that true?
yes. That's what we call superposition. It's a really mind-bending concept, and it gets into this wave-particle duality thing. It means at that really small level, particles like electrons can act like both a particle, which has a set location, and a wave, which is spread out.
So they're not actually both things at the same time, right?
Yeah.
But they can act like either, depending on how we look at them.
Yeah, that's the basic idea. It's one of those things in quantum mechanics that's just really hard to wrap your head around. But think of it this way. An electron doesn't really have a definite position until we measure it. Before we measure it, it's more like a wave of possibilities spread out over space.
So it's like it's in this blurry state of maybe being here, maybe being there, and then when we measure it, it's forced to choose a spot. That's wild. So does that mean that we're actually affecting reality just by looking at it?
Yep. That's one of the fundamental things about quantum mechanics. The act of measuring something can actually change what you're measuring. It's one of the things that makes the quantum world so counterintuitive.
Okay, this is starting to make my brain hurt a bit. But I think I'm starting to get a better idea of the rules of the quantum world. So we've talked about atoms and those tiny particles. Is there like a point where these quantum effects start to disappear and things start to act more like the normal physics we're used to?
Well, there's kind of an in-between zone. We call it the mesoscopic scale. And it's where quantum effects can be seen in things that are bigger than single atoms, but still super tiny.
So what kind of things are at this scale that act all quantum weird?
One really good example is quantum dots. They're these teeny tiny semiconductor crystals, only a few nanometers wide. They're so small that their electrons are kind of trapped, and that creates these quantized energy levels, like the staircase we talked about.
So they're like mini atoms, but we can control them.
Exactly. The really cool thing about quantum dots is that we can change their properties, like what color of light they give off, just by changing how big they are. It's like fine-tuning color with atomic level precision.
That's insane. What kind of things can we do with that kind of control?
Well, quantum dots are already being used in things like high-definition TVs and computer screens to make the colors super vibrant and accurate, but the possibilities really go way beyond that. Like, they could be used in solar energy and medicine.
Wait, you're saying these little dots could change how we get energy and treat diseases? How?
Imagine solar panels that can grab way more of the energy in sunlight, making them way more efficient. Or think about tiny quantum dots carrying medicine directly to sick cells. That's just the beginning of nanotechnology powered by quantum mechanics.
Wow, we've gone from electrons jumping between energy levels to controlling matter at the nanoscale.
Yeah.
That's a lot. But is that the limit?
Yeah.
Can quantum effects show up in the world we see every day? like in big objects?
Yeah. It might surprise you, but the answer is yes. Sometimes quantum stuff can affect really big things. And one of the coolest examples is superconductivity.
Superconductivity. That sounds familiar. Something about electricity flowing without any resistance, right? But how does that have anything to do with quantum mechanics?
When you get down to really, really low temperatures, close to what we call absolute zero, some materials do some really weird things. Their electrons start to pair up in a special way, and that lets them move through the material without getting scattered or losing any energy.
So it's like a perfect highway for electrons with no traffic jams. What does that allow us to do?
It could change everything. Imagine power lines that can move electricity across huge distances without losing any power, or super powerful magnets for medical imaging, or even levitating trains.
Levitating trains. Are you talking about trains that float above the tracks? That sounds crazy.
That's already happening. Superconducting magnets can create such strong magnetic fields that they can actually lift a train off the track. So yeah, levitating trains are real.
This is blowing my mind. But if quantum mechanics can do all that, even with big stuff, why don't we see it all the time? Why does most of the world seem to follow the rules of normal physics?
That's where decoherence comes in. As things get bigger and more complicated and they interact more with their environment, those quantum connections that make the weird stuff happen start to get messed up.
So it's like all the quantum weirdness gets washed away as things get bigger.
Yeah, that's a good way to think about it. In a big object like a baseball, there are so many atoms, trillions and trillions of them, all bumping into each other. And all that interaction basically destroys the quantum coherence, so what we see is normal classical physics.
I see. So the quantum world is still there, but it's kind of hidden under all the chaos of a big object, like a whisper getting drowned out by a crowd.
That's a great analogy. But even though we don't always see it, quantum mechanics is running the show. It's what makes our modern technology possible.
I know. It's kind of mind-blowing. It's like this secret layer of reality controlling everything, and we're just starting to understand it. I can't wait to dive even deeper.
Me too. Let's explore some even weirder stuff next time.
Sounds good. I'm ready for more.
One of the things that's really exciting right now is quantum computing.
I know. I keep hearing about it everywhere. It sounds like it's going to revolutionize how we use computers. But I'm still not really clear on what makes it so different from the computers we have now.
It all boils down to how information is stored and processed. Like in regular computers, we use bits. And a bit can be either a 0 or a 1.
Right, that's the basic building block of all digital information.
But in quantum computers, we use qubits. And qubits take advantage of superposition.
Ah, superposition. That's where a particle can be in multiple states at once, right? How do you use that for computing, though?
Think about a qubit like a coin that's spinning in the air. Until you stop it, and look, it's not heads or tails, it's kind of both at the same time. Now imagine a bunch of these qubits all spinning together. They can be in a superposition of all possible combinations of zeros and ones at the same time.
So instead of just two states like a regular bit, a qubit can be in a ton of states at once. That's crazy.
Yeah, that's what makes quantum computers so powerful. They can explore a huge number of possibilities simultaneously, something normal computers just can't do.
So what kind of problems can we solve with this kind of parallel processing power?
One area where it could be really huge is in drug discovery. Trying to simulate how molecules interact, especially big, complicated biological molecules, takes a ton of computing power. But quantum computers could make that process way faster.
So we could develop new drugs and treatments much quicker.
Exactly. And it's not just medicine. Quantum computers could also be used to design new materials with specific properties, like strength, conductivity, or heat resistance, by manipulating them at the atomic level.
Wow, that sounds like we could build materials from scratch with exactly the properties we want.
Pretty much. And then there's artificial intelligence. AI relies on these algorithms called machine learning algorithms, which process huge amounts of data. Quantum computers could speed those up significantly.
But so quantum computing could revolutionize healthcare, materials science, and AI. That's a pretty big deal. But if it's so powerful, why don't we have quantum computers everywhere yet? What's the catch?
One of the biggest challenges is that darn decoherence. Remember how we talked about how quantum systems are really fragile and easily messed up by their surroundings?
Right, those superpositions are easily disrupted.
Well, that's a huge problem when you're trying to build a quantum computer. Keeping those qubits in their quantum states long enough to do any real calculations is super difficult.
So it's kind of like trying to build a house of cards in a hurricane.
Yeah, kind of. Creating a quantum computer that's stable and reliable is a huge engineering feat.
I see. So we're still in the early stages, but the potential is huge. Any idea when we might see these quantum supercomputers become more common?
It's hard to say for sure. Some experts think it could be decades before we have really large-scale, reliable quantum computers, but things are moving really fast. Who knows what the future holds?
It's exciting to think about. Okay, so we've talked about quantum computers, but there's another mind-blowing thing I wanted to ask you about. Bose-Einstein condensates. What are those exactly?
A Bose-Einstein condensate, or BEC for short, is a really special state of matter that happens when you cool down a bunch of atoms to super low temperatures, almost to absolute zero.
Absolute zero. That's like colder than anything we can find naturally on Earth, right?
Yeah, it's incredibly cold. And at those temperatures, something amazing happens.
That makes sense.
The atoms basically lose their individual identities and start behaving like one giant quantum object.
So a bunch of separate atoms suddenly become one big superatom. How is that even possible?
It's one of those things that only happens in the quantum world. At those incredibly low temperatures, the wave functions of the atoms, which describe their probabilities, overlap and merge. It's like they all become part of the same wave function and act together.
So even though BEC has billions of atoms, it acts like one giant quantum object. That's crazy.
It really blurs the line between the microscopic and macroscopic worlds, and BECs can exhibit some wild quantum behavior, like superfluidity.
Oh, superfluidity. That's where a fluid flows without any resistance, like a perpetual motion machine for liquids, right?
Right, and BECs can do that. They can flow through tiny cracks and spaces without losing any energy to friction.
It's amazing that we can actually create and study these bizarre states of matter in labs. It makes you wonder what other weird things are out there in the quantum world. It's crazy to think that something as basic as temperature can change how matter behaves. So is there like a hard line where the quantum world stops and normal physics starts?
Not really. It's more like a gradual shift. As things get bigger and more complex, it gets harder to see quantum effects, but they never really go away completely.
So even in the everyday world, there's still a bit of quantum weirdness going on.
Exactly. Think about it. Every time you flip on a light, use your phone, or even see the colors of a sunset, quantum mechanics is at work.
Okay, give me an example. How does quantum stuff affect something like a light bulb?
Well, let's take an old-fashioned incandescent light bulb. The filament, that little wire inside, glows because it gets really hot. But the way it gets hot and gives off light, that's all because of quantum mechanics.
So those electrons moving around in the filament, absorbing and giving off energy as the photons, that's all governed by those quantum rules.
Exactly. If it weren't for quantum mechanics, we wouldn't have light bulbs.
It's like there's this hidden code, a quantum language, that makes the universe work. And we're just starting to figure it out.
That's a great way to put it. And the more we learn about this code, the more amazing things we can do.
We've covered so much already. Quantum dots, tunneling, superconductivity, even those Bose-Einstein condensates. It feels like we're just scratching the surface of what quantum mechanics can do. What are some other areas of research that are really pushing the limits?
One area that's super exciting is quantum cryptography. It uses the principles of quantum mechanics to create communication systems that are basically unbreakable.
Unbreakable? That sounds like something out of science fiction. How is that even possible?
It's based on the idea that if you try to eavesdrop on a quantum communication channel, you'll mess up the quantum state of the particles that are carrying the information. And that mess up will tell the sender and receiver that someone's trying to listen in.
So it's like a built-in alarm system that's protected by the laws of physics.
Exactly. It's pretty cool. And then there's quantum metrology, which uses quantum systems to make extremely precise measurements.
Are we talking about clocks that can measure time down to like a billionth of a second? Or sensors that can pick up tiny changes in gravity?
Yeah, things like that. Quantum metrology could revolutionize fields like navigation and geophysics. It could even help us detect gravitational waves or test some of our most fundamental theories about the universe.
Wow, it's amazing that we can use quantum mechanics to make such incredibly precise measurements. It opens up a whole new world of possibilities.
And that's really just the tip of the iceberg. The more we explore the quantum realm, the more we realize how much we don't know. It's a universe full of mysteries, and quantum mechanics is the key to unlocking many of them.
It's been an incredible journey exploring the quantum world with you today. From the tiniest particles to the largest scales, quantum mechanics shapes reality in ways we can barely begin to understand.
And the best part is that it challenges our intuition every step of the way. It forces us to rethink what we thought we knew about the universe.
I couldn't have said it better myself. And to our listeners, thanks for joining us on this deep dive into the quantum realm. Keep those minds curious, and we'll see you next time for another adventure into the unknown.